Hello, thank you very much. I want to present my paper. The name of the paper is Code as the Expression of Its Own Vitalism. I will read it. Introduction. In the mid-50s of the 20th century, when computers and computer languages were just beginning their fantastic development, a group of creators and artists produced a series of works that are now called concrete poetry. In these works, physical and formal aspects of language, such as phonetics, typography, and spatial arrange, punctuation marks, etc., along with other principles of formal languages, such as generativity and algorithms, are fused and interspersed with the pure literary expression built over centuries of history of oral and writing human communication. It was within this extensive and eclectic ecosystem of writers, graphic artists, and audiovisual performers in which I started to imagine how can formal languages, such as computer programs, can deal with the so-called artistic expression. I wrote a little paper about the musical formal arrangement and oral implications in the work of Argentinian writer Oliverio Girondo in 2004. So a direct path to code was almost obvious, and I was soon programming my own algorithmic music. This paper is an introduction to a further development in which I will try to discuss some of the key concepts that I have been developing since that, both from an empirical point of view and with the support of contemporary knowledge on digital media and philosophy of technology. The score. Perhaps the first and most obvious comparison between a piece of code and a musical object can be seen in the score. Musical scores are composed of a system of symbols and rules, and by this means can contain the representation of the temporal display of an abstract sound pattern. Following this approach, the musical canon, and most precisely the enigmatic canon, represents for me a beautiful example for such a cryptic formal system, intended to be also a piece of music. I carry on with an old school fascination with enigmatic canons, so in 2013 I started to code snippets of infinite generative sonic structures with SuperCollider. I was immediately engaged by the way in which a small amount of code or symbols can contain potentially endless music, loaded also with its own meaning. I started working on exploring the boundaries of the pattern library in SuperCollider, but after that I focused on demand fusions and the GitLib library, mostly because of the need to manage a shared set of raw data between multiple patterns, or simply to generate or transform that data in real time. In example 1, for example, you can see the code for track 1 node proxy holding a function to generate a musical pattern from a set of predefined arrays of data. So enigmatic canons are often based on mathematical relationships between voices, such as proportional tempos or intervallic transformations. So I coded a dictionary of custom functions to serve this purpose. In example 2, successive calls to different functions that generate or modify data, array data. Yeah? And in example 3, you can see, for example, a dictionary hold a custom function to operate over arrayed sets. In this case, the function split values on a write, generating two different new values related with one each other with the golden ratio. So these codes are, as scores, a blueprint for performers providing all the necessary information to play the music as intended by the composer. But they are not for human performers. Instead, the performer is a computer. In Renaissance, enigmatic canons helped push the boundaries of musical composition, exploring new possibilities for structure and expression. Today, I find the same paradigm by writing these code snippets, exploring them as containers for its own, maybe infinite sonic enigma. The instrument. Another huge and interesting path can be traced through the concepts of machine, musical instrument, and code or algorithm. This is by sheer logic an enormous amount of work that can easily reflect the very history of the human being. So in order to focus on some very personal point of interest, I choose the Simondonian concept of technical object to order my thinking and serve as a conceptual basis. My fascination with music and machines grew at the same moment, in the same act, watching my 80s favorite stars make incredible futuristic sounds flow from the black boxes with fluorescent buttons called synthesizers. This influenced my future interest in two very specific areas, music and technology, and shortly after the brain explosion of delving into Franco-Flemish polyphony and ultimately on Bach's logical counterpoint, in the early days of the web, I discovered a piece of software called maybe AETM3-3, or for me, simple Outtaker generative sequencer. I think I found this max patch in 2004 or 2005, and despite conjectures about its origin or authors, I spent hours listening to its continuing evolving flow of synthetic sounds and melodies. I started to imagine the future of the musical objects as just pieces of data and logical information packaged on very little binary files containing an endless amount of music capable of being interpreted by any computer on the world and beyond and easily shared over digital nets. Back to Simondon, for him, a technical object is not just a tool or machine, it is a system that undergoes development and adaptation over time. It has a life of its own, shaped by its internal logic and its internal interactions with its environment. Outtaker generative sequencer, it is essentially a max MSP patch. In such a graphic programming environment, a button or a number box can be something fully automated or something over which someone can apply a deliberate action to trigger some sudden formal disruption or some subtle timbral modulation. Moreover, a very interesting issue around this process of tweaking over the algorithm behavior is that the musical experience becomes a two-way conversational process between the machine intrinsic logic and the human ear or musical hearing. This hybridization between machine and musical instrument or interface becomes a main subject of research in my work. So in this example number 4, we can see how we can inject control node proxies into track 1 to modify it and add some line control over some inner parameters, yes, with this CC node controls proxies. Composition. To address this question, I will mention the work of Fredrik Olofsson. His SuperCollider tweets aroused my curiosity to investigate the potential hidden in these short code snippets. And as he says, to get inside the structure of a particular piece of code. A particular piece of code that is like an enigmatic container for a possible endless range of sounds carry on with its own meaning. He refers to these musical objects as miniature compositions and describes the compositional process as a mind-machine feedback loop. I mentioned this concept earlier when I talked about the two-way conversational process involved in tweak the algorithm while it is running, and I will address it again later when I will talk a little about performance and live coding. Yep. Olofsson argues that my mind and my computer's CPU are like coprocessors, or like two halves of a brain, working in tandem on the same problem. One is dealing with the given problem in theory, and the other in practice. The same algorithms are running both on the computer and in my mind. They are working in parallel, but in completely different ways. Compared to the CPU, my brain funnels out and deals more with predictive evaluation processes linked to how the code could or might sound. It takes into account what just has happened and future possibilities. The CPU, on the other hand, does not do any of that. It just autonomously executes the work here and now and aware of what it is doing. It is concrete and plays its part in the larger system, the mind-machine feedback loop. Performance. At this point, the compositional process becomes deeply intertwined with performance. Moreover, similarities with other musical systems, such as modular synthesizers, can be considered. From this idea, I started to think about a so-called by me hybrid system for my performance setup. In this hybrid system, two different subsystems that share many common properties work together by exchanging information, resulting in a single common output. I started to be fascinated with the idea of write codes that can trigger and or generate signals to be routed to a modular synthesis system. While this concept is perhaps not new, the motivation behind this search is to adopt the idea of a live-coded modular synthesizer. This is controlling analog signals not just by tweaking knobs and buttons, but also by writing and modifying codes on performance. So this picture illustrates how this setup is seen from the hardware side. This setup is for the live performance with my project on Xcoder. You can see my computer with SuperCollider and a MIDI controller and a modular synth. Example 6. This is a very simple node proxy generating a two-channel signal to control both CB and gate and on an analog synthesizer. And in example 7, a live coded session flow that shows how a single node proxy is used to carry on different kinds of frequency modulation on an analog instrument, for example. Live coding or conversational programming is generally described as the act of write or modify the source code of a program while it is running. This is a very contemporary practice carried on by artists around the world making music, visuals, and other performance arts. And this practice can be achieved in SuperCollider with a couple of different techniques. However, mastering live coding in this language is a challenging task. As I mentioned it earlier, I prefer to use the GitLib library and the proxy space paradigm. By this means, I can work with a number of nodes to live code on and a set of environment variables to share that data between these nodes and to hold other globally accessed information such as MIDI or open sound control connections, clocks, etc. I also use environment variables as dictionaries to hold audio files and custom functions to generate or modify arrangements of data. In this particular approach, code as a system of symbols and rules and live coding as a practical solution are working as the glue that serves to give formal structure to the complex musical ecosystem shared by the score, composition, instrument, and performance. As a conclusion, the intellectual effort of ordering the ideas and tools related to an artist's work is a task that we do not always entrust to ourselves. However, it is an invaluable exercise, especially for those of us who work in a close link with today's technological tools. In relation to my work, it has helped me to build a retrospective and to understand how the techniques I use today, especially music computing and live coding, relate to my musical history. Thank you very much.
I already mentioned this social thing, and for me, SuperCollider from the beginning was a tremendous space for learning, making friendships, discussing, collaborating, and I think this is also quite important element of what programming can be about. In terms of also kind of thinking a bit more broader about programming for artistic purposes or programming for compositional purposes, there is also this idea of somehow encapsulation of a worldview or a compositional methods, and these elements were quite important for my PhD project, which I completed a few years ago in Edinburgh. And the project dealt with this implementation of a sound synthesis technique called Pulsar synthesis, and also rewriting of this historical digital instrument or program, also which was developed in SuperCollider 2, called Pulsar generator. I wasn't very inventive in this sense. I called my program the new Pulsar generator. So that's what you see. And what I would like to focus on today is to talk a little bit more about this aspects of programming, which and the artistic practice which deal with this idea of a computer program as an artifact. So I think I said all of these things already. One of the kind of key aspects of what I think when I think the word artifact is this that artifacts are something practical. You touch them, you could view the world through them. So in a sense, they create this kind of apprehensions, you know, that, and the artist or the maker of the artifact or artist through the use of the artifact, you know, generates these apprehensions, you know, which could present a new way of seeing, hearing, and seeing the reality. And for me, you know, developing this software, but also engaging with the original software, which was developed by Curtis Rhodes and Alberto Di Campo, also meant that I engage with this kind of wide knowledge generation process, and also trying to think what sort of world or a compositional set of possibilities this kind of program allows or not allows. How does it open certain possibilities, and how certain possibilities are closed? And also, on this purely kind of cognitive or epistemic level, thinking about these ways of seeing, hearing, and sensing the reality which the computer program could support. Obviously, I made more notes than I need. So this is the original Pulsar generator. It was developed in SuperCollider 2 and distributed as a binary. Was written by Curtis Rhodes and Alberto Di Campo. Alberto, who was planning to be here, sadly he didn't make it. Curtis, who is a soon retired professor in Santa Barbara, was also external advisor on my PhD project. And kind of funny thing about this development, and it also relates to some of these discussions we had on the kind of outskirts of Lucille's keynote. This idea of preserving the software and how long the software kind of lives. There's a funny story about this particular development that the moment software was released and Curtis and Alberto tried to sell the copies of software to artists to distribute it. Within 2 to 3 months, Apple changed the whole architecture of their system and moved from OS 9 to OS X. So the software became obsolete pretty soon. And yeah, obviously that kind of limited the possibility for it to be used by kind of broader variety of artists, audiences, publics. Nonetheless, the kind of sound of this particular technique and the kind of program implementation of it is something which brought me into this particular development first of all, but then to SuperCollider too. And this is one thing I always say, that often the kind of experience of music and kind of engagement with the kind of material traces of how this particular music is made can lead one to learning programming language, and then in reverse, like learning programming language could allow one, in this case myself, allowed me to engage with a kind of broader history of computer music, of a kind of particular conceptualization of sound. In this context, this kind of granular or microsound type of formalizing musical sound. So I thought that it's really interesting that the software or the program could be this sort of a vessel or a lens through which one can kind of proceed into different areas of practice. And in a sense, the way I view my work, also the kind of artistic work which you had a chance to sample yesterday, and my academic research work is in this context of media archaeology, within which I kind of mediate through, like, on one hand the composition aspects of my work, on the other hand the computer programming, and try to kind of find a synthetic view of different complex relationships between these two fields. Let me just go further. I said all of these things already. So yes, so you software is like the original process. There were a few release the background and code structure. So part of my development was kind of kind of open it up in a sense that the code would become an interface. So I think there's also this relationship between the surface and the kind of the deep level of the program, which could be the code, and the surface, which is the graphic interface, is also something I engaged with in a sense of trying to bring the text into the foreground and treat the text as an interface. Next stage is this like kind of further complication, and you may see my work as this kind of going further and further and complicating my own practice and life as a result. Because you have this program, you have this interface, but then when you think about what it is, pulsar synthesis, what is the pulsar generator, you start to gather this material traces. On one hand, you have this original SuperCollider 1 script, first sketches. I also have somewhere like sketches in Symptomatic, which Curtis also did in kind of early days of kind of implementing the idea. So almost from the beginning, the conceptual and material emergence of the technique of pulsar synthesis and pulsar generator were linked with Symptomatic and SuperCollider. So you can't really separate the technique and what it is, how it sounds like, from the kind of larger infrastructure of the programming. On the other hand, you have this whole field of kind of diagrammatic circuit sketching, which also contributes to the kind of definition and redefinition of the software. And kind of another layer of this kind of diagrammatic thinking, which contributes to conceptualization of the technique, is this kind of further representation of sound in a particular way. In this sense, this kind of corpuscular or granular, like a view of sound and what sound could be. So treat sound in micro scale, micro temporal segments. What I do as an artist and as a researcher is dealing with these different temporalities. So pulsar generator operates in time, like all the processes, all the aspects of the way the program functions happens in time. And there are kind of peculiar ways of how time is kind of defined or could be understood through that program. And I found it really fascinating to think about these different temporalities. You have these music theoretical conceptualizations of time, like kind of musical time, phrases, forms. That's why I was really interested in James's yesterday keynote when he was talking about this pure form in the context of his new programming developments. I often ask myself, what are these kind of pure formal or the kind of primitive formal things, objects? Maybe object is already something formed. So like the thing, what is this primitive thing and sound in general, but in pulsar synthesis, and you may think that maybe it's this thing, this pulse as a kind of most primitive element of it. But I kind of tend to go kind of a little bit back, but also deeper from a different angles. If I go back to the previous slide, I think of these empty tables, which are of the size 2048 values, as the kind of the most kind of basic level of the kind of temporal definition of what pulsar synthesis and pulsar generator and in relation to that, the new Pulsar generator deals with this this is the kind of the lowest formal unit, you could say. Then move to our open deployment and see maybe yesterday, and also concludes this idea of what I deal with when I deal with this. There's this media theory scholar, Wolfgang Ernst, who writes about technology, but from this perspective of media artifacts. And one aspect of what he highlights in terms of us engaging with an old technology is this aspect of making this technology operational. And that's what I often think about code. You know, obviously there's a whole field of this kind of hermeneutics of code, kind of code studies, which deal with the text itself, but you can't really separate the text from what it does, you know, and especially in the context of music, you almost want to or need to hear the code in action. And there is this really interesting positioning of these different archaeological perspective. Archaeological and technical is when one way that can looked at, you know, one way which can be extracted by breaking the vase, and somehow that's what I've been also trying with the computer program, trying to break it and make it do different things. But what radio or a computer requires is that it reveals its essence by monumentally, it doesn't reveal its essence by monumentally being there, but only when processed by electromagnetic waves or calculating processes. So Ernst uses this example of a radio, and actually in his other writing, he talks about a particular radio, a radio which was mass-produced during Third Reich in Germany, and whether that radio has a different meaning or value now, broadcasting kind of current radio signals. It's something quite interesting. But this aspect of generative like as program or computer as a generator of this sensual and informational presence is something which I feel kind of summarizes my work. So maybe I should have started with this slide and just highlight the bottom sentence and then finish. So this is the time for me to just open the program and like show you a little bit, and then we can move to questions. So I'll try to do it. I will share the GitHub with you later, so you can download it. There's in development. I'm going to develop it as a Quark, so it will be easier to kind of maintain and also update. But as you see, the new Pulsar generator inherits a lot of the look from the original Pulsar generator. And this is kind of another aspect of the kind of design which I wanted to engage with. The original Pulsar generator used this color scheme. You know, you see this kind of greenish color is from these old hardware testing machinery by Kreil and Ruel. So I use the same color scheme. Also, this idea of kind of object-oriented design, like having the same kind of table object, you know, these things here, but just playing different role depends on where are they placed in the system, was something which appealed to me. But as I said, the program on the surface may look similar to the original one, but I wouldn't think about it as a new implementation. I would think about it as a, distant cousin of the Pulsar generator. It manages to make the same sounds as the original one because we also to use them out the Elazons, the Schmickler, and her also has well. So part of this process was also to these presets and compare the output. And in one of the kind of early versions of the program, I managed to match the output of the both softwares, but that wasn't the main goal. My main goal was to make music with it, and maybe I should have said it from the beginning. Like that's my main activity. So if someone's gonna write me an email saying like, "Oh, this doesn't work," yeah, I know it may keep not working forever because sometimes I fix things, or I change them. I'm really bad at maintaining like version control and so on. So I'm not a good seller, but that's you take it, you play with it. There's the community around it, people who recorded music with it. There are like 3 volumes of like compilations. So there is already quite interesting community, but you have to be willing to deal with the kind of the worldview I'm giving to you. But also because you can reprogram it, it allows you to have some agency there. You can break it yourself, for example. So just shortly, I'll just show you maybe like so you have this tables. They define the pulse. But sound here, so I don't know if this is should I let me
You have to go.
yeah, so yeah. So I'll do it here. And it was this AV bridge, yeah. Yeah, sample rates. So yeah, so it starts with this, like original program also didn't make any sound when you started it. You had to define these 2 basic things, which is the envelope and the pulsar waveform. And they are basically multiplied. So the envelope limits in time the pulsar waveform. And it defines this kind of lowest level thing, the pulse. It's very similar to grain and the granular sound concept. And there's some lag. But what happens with the pulsar synthesis is like you have this pulse which gets repeated at a particular rate, the fundamental frequency. And one of these discussions about temporality and the compositional sense is that by speeding up this pulse, you are cutting to the threshold of discrete pulses to the rhythm. And it's a kind of well-known phenomena, at least from like 1950s, where Karl-Heinz Stockhausen described it in one of his papers, How Time Passes, but also like implemented it in one of his compositions in Contactor. So by speeding up this pulse, we have another set of tables to control the development of parameters and kind of mesoscale. So yeah, there's microscale where you define the let's say timbre or color of the sound. And then you have this mesoscale where you tell for different parameters how they should behave in time. It's pretty close to original Pulsar generator, but what I didn't know when I started designing the software and kind of playing with it was that by going a bit more deeper into the parameter space, so not super low level of programming, but basically looking at the original synthesis definition by Curtis and Alberto, and by kind of intervening in between the way they map parameters or they set the ranges of the values, I could get totally different sonic outputs. And one of the kind of interesting things which I discovered by simply treating the kind of envelope slightly different than the original one, it was, and also adding some modulation. Something you wouldn't get in the original Pulsar generator. This kind of like almost like bell synthesis, and this only kind of happened by experimenting with the program and kind of reprogramming the synth. So the whole infrastructure behind the interface is based on GitLib. So it's fully compatible with all the GitLib possibilities. So for example, run this like kind of effect processes on top of the output. This was the sound which actually brought me to this program, and it's the type of sound I heard on the release by Marcus Schmickler, Authors of Science, on track number 6. That's really kind of digital, but also super organic kind of sound, which sounds, I don't know, like crunching. And implementing it in here was such a great pleasure for me to then also go back to the artist and say, here, I made this sound. It sounds like the stuff you did. And that's where I'm going to finish. Thank you.
About the inherent limitations of the interface. I'm thinking about connecting this with the bigger conversations around more standard synthesis like accessibility, CPO, override results. Have you usually, minute changes in a parameter can have all sorts of effects across different character explosions? Have you been thinking about a more maybe embodied way of accessing these spaces? Because this is maybe my personal kind of gripe. It's just that I often find with these kinds of interfaces, trying to find those sweet spots can be quite time intensive and, etc. I'm just wondering about the possibility of opening up a different kind of interface that can access these kind of topologies.
Yeah, I mean, it's obviously it's possible in the sense that the infrastructure of like SuperCollider allows it, and I did like work with my students where they connected with this software with like sensors. Obviously, you can control it with MIDI. I want to like move as little as possible when I especially when I play. So like I often even don't have this graphic interface open. I just on text. But yeah, it's possible, to connect MIDI to it. It's super easy, and some people do it. I've never used MIDI controllers, and there's a story like when I started studying, I could hardly afford to have a laptop. I was working on a borrowed laptop for like 2 years, and each of these MIDI controllers like also cost money. And I remember like I tried one, didn't do what I wanted. I tried another one, and I felt like this is another wallet draining thing. So I just like decided to just like stick with whatever I had at that time, and kind of made it work. But it's also like this part of the interface. It's also interesting from a compositional perspective that there is this kind of historical reference that it looks the way it looks, allows to do certain things, it doesn't allow to do other things. But it's also interesting kind of engaging with the constraints of the kind of material and tools which are there. I think I think that's what makes me interested in like doing things, is to do it differently. But yeah, all these things like trying to kind of like experiment with this tool and with different approaches. It's possible. Like recently, I did in a class when we were talking about Flucoma, for example, and the possibilities which Flucoma gives for parameter reduction and kind of control of multiple parameters with just kind of with 1 or 2 values. We also used like Flucoma to kind of do this parameter reduction and then control the kind of 2-dimensional space with just kind of like with the video tracking. Yeah, it does. Then it does different things. It's interesting. Like what really made me super exciting about this, like one version of this program, which looked slightly different, which I released in 2017. That a lot of people started using it, and it was mainly because of these artists I already mentioned, that people someone want to sound like them or want to explore the same techniques. So they started kind of experimenting with one of these versions I released, and they started like putting out their music, which sounded totally different to what I would do with the software. And I found this really exciting that this like going back to this temporalities aspect of this work, that there's this compositional temporalities, these digital temporalities, like real time, what is real time, what is non-real time, and also these human temporalities, like me dealing with the historical artifacts, like spending my now time with it, but also projecting it to the future and giving it to other people to do it. So if you want to like hook it up to some fancy sensors, I will be happy to to support you. Thank you. Thanks a lot.
Invitation by Stefan Merritt, who will not be joining us because it's the middle of the night where they are. So it's in the video, which we will play.
Hi.
Ted,
Yeah.
I don't think you've turned on the sound sharing.
Oh, good.
I might be wrong, but.
O'Hara, currently a PhD
Sorry.
student at
I was like,
Sensei
where's my
Monash
phone?
University in Melbourne, Australia. I'm
This was
Hi, my name is Steph O'Hara, currently a PhD student at SensiLab, Monash University in Melbourne, Australia. I'm delighted to share my work on live coding and AI assistance for dynamic musical instrument design in SuperCollider, an approach I developed during the Soundtree project, a 6-month ethnographic engagement culminating in a public performance. I would like to begin by acknowledging the traditional custodians of the land on which I am speaking, the Wurundjeri, Woiwurrung and Bunurong peoples of the Kulin Nation. I pay my respects to their elders past, present and emerging, and extend that respect to all Aboriginal and Torres Strait Islander peoples. Before diving into the technical aspects, let me introduce the Soundtree project. This was a collaborative endeavour, bringing together 5 performers with diverse movement capabilities and 2 support artists from a community-based arts organisation. The project centred around an accessible sound sculpture, the Soundtree, where digital instruments coexisted with traditional sound-making objects. The primary interface I used was the AirStick, an established accessible digital musical interface developed at SensiLab. Each AirStick contains an ESP32 microcontroller and an IMU sensor, transmitting real-time movement data over Wi-Fi using OSE. The performance setup integrated multiple AirSticks connecting to several central Raspberry Pi 5 hubs. Each hub processed the movement data and ran SuperCollider, enabling real-time gesture to sound conversion. The AirSticks are small enough to be worn or embedded in various materials, balls, fabric and suspended strings, creating tangible instruments with different affordances for movement. The beauty of this arrangement was that performers could design ways to interface and interact not only through direct manipulation of their instruments, but also through the physical arrangement of the Soundtree itself, creating layers of interaction between acoustic and digital elements. Within the workshop environments, performers could explore real-time mappings between gesture and sound, experimenting with sound design parameters that responded instantly to their movements, allowing for collaborative creation and immediate sonic feedback as they developed their unique performance language. Now let me explain with the challenge I faced. How do I create accessible digital musical instruments that can be rapidly personalized for diverse movement capabilities while maintaining collective musical coherence? Traditional approaches to ADMI design often rely on pre-configured mappings developed before performer engagement, while existing solutions support individual needs through custom interfaces or control mechanisms. They typically require technical expertise and development time between iterations, interrupting the creative flow of workshops and potentially limiting performer engagement. My solution centers on what I call personality files and a shared community data structure. A personality file encapsulates everything needed for an instrument: synthesis definitions, mapping relationships, control behaviors, event handling logic. Importantly, these aren't static definitions. They're dynamic code that can be modified and reloaded during workshops using SuperCollider's live coding capabilities. Each personality connects to a shared community data structure that maintains musical parameters across instruments like tempo, root notes, and energy levels. This dual approach enables both individual expression and collective coherence. The technical framework I developed in SuperCollider used several key concepts to enable dynamic instrument creation and modification. Each personality file was implemented as a separate environment, creating a namespace that encapsulated all functions, variable, and synth definitions. This provided crucial isolation between different personalities, while allowing for specific shared elements. The environment approach allowed me to interpret entire personality files on the fly, enabling real-time adaptation during workshops without disrupting other performers. When I made changes to one personality, the others remained stable and continued playing. The mapping system was perhaps the most creative element. Rather than simple one-to-one mappings, I used mapping functions that transformed sensor data through multiple stages. Firstly, pre-processing, applying dead zones, thresholds, and noise reduction. Secondly, response shaping, using non-linear curves to shape and refine mappings. Thirdly, range adaptation, scaling to performer-specific calibrated ranges. Fourthly, temporal processing, adding smoothing, acceleration detection, and historical context. And lastly, musical mapping, converting process values to musically relevant parameters. These mapping functions were themselves subjects of live coding modifications during workshops, allowing me to fine-tune response curves, scaling factors, and filter characteristics based on immediate feedback. The community structure was implemented as shared data, allowing personalities to both read from and contribute to collective parameters. Personalities could subscribe to notifications of parameter changes, enabling responsive ensemble behavior while maintaining individual expression. The integration of a large language model was really valuable for sound design. Expanding the creative palette with synthesizer definitions I might not have otherwise explored. Enabling rapid prototyping through text prompting by describing types of synthesis architecture within a prompt to generate scaffolding code. And using prompts to express different ideas brought up in the workshops. Natural environments such as ocean, wind, trees, rain. The large language model gave me an initial synth which well-defined filter parameters and signal routing, so I was able to quickly refine the synth for use. One particular successful technique was using a model to regenerate synths by passing previous generated synth code back as part of the next prompt. This provided a way of evolving a synth design while storing each iteration for later use. Interestingly, errors in routing or bad filter use would result in these errors also being passed on to newer generated synths. Using an LLM to generate a synth definition provided an approach that might not have been my first instinct, but that often yielded expressive results. Along with co-designing both these sonic personalities and mappings within a workshop rehearsal environment, I was able to provide a space for exploration and finding magic moments. This technical approach offered significant benefits. Firstly, incremental modifications. The system allowed modifications to specific elements without disrupting the output. Refinements of mappings were easy and creative. Secondly, mapping chains. Using multi-stage mapping functions enabled complex relationships between movement and sound that could also evolve over time. Thirdly, immediate adaptation. SuperCollider's evaluate and replace capabilities meant I could modify any aspect of synthesis to mapping to logic in real time. And lastly, LLM assistance provided a tool for fast iteration of sound ideas based on performers' ideas or needs. More time was spent on refining these sounds rather than building them from scratch. Through sustained co-design, each personality file evolved to match a performer's specific capabilities and preferences. These instruments became so tailored to their creators that they could only be effectively played by the person for whom they were designed. Yet simultaneously, the community structure allowed these diverse instruments to function together musically. Of course, I faced challenges. Firstly, the technical robustness. The continuous development and modification of the system sometimes led to instability, requiring restarts. Despite this, a restart often only needed code to be reinterpreted. Secondly, resource management. Multiple environments with synths, controlled data processing, and a GUI running simultaneously created significant CPU load on a Raspberry Pi, requiring optimization. And thirdly, code management. The flexibility of changing code meant I sometimes lost something that happened within a live coding moment. Incremental auto commits is something I would like to look into. Despite these challenges, the approach proved successful in supporting both personal and collective musical expression, culminating in a public performance where participants with diverse movement capabilities express themselves within an ensemble environment. I'd like to highlight three broader implications of this work. First, reconceptualizing code as an expressive medium rather than just a technical implementation tool. The personality files represent a novel form of ADMI, where code becomes an artistic expression tailored to individual needs. Second, the integration of AI assistants into instrument design suggests new paradigms for ADMI development. While my simple implementation focused on synth generation, future applications could include conversational instrument design interfaces, adaptive mapping suggestions based on movement analysis, and personalized learning pathways. Third, I believe accessible co-design principles should inform software architecture decisions. Rather than treating accessibility as a feature added to existing systems, centering accessibility in software design leads to more flexible, responsive, and creative systems. Looking forward, I see several promising directions. Firstly, accessibility-focused UI layer. Developing graphical interfaces as performance interfaces, while maintaining the flexibility of the underlying SuperCollider system. Currently, I am working on the hub performance interface, so performers can take home and practice playing the air sticks. Secondly, extended mapping frameworks, building on my multi-stage mapping approach to create higher-level abstractions that are more intuitive to modify. This will also expand using new sensor inputs including touch, bend, flex, pressure, and buttons. And thirdly, more sophisticated AI integration, moving beyond synth definitions to AI-assisted pattern generation and structural composition. In conclusion, the Soundtree project demonstrates how the integration of live coding, thanks to SuperCollider, LLM assistance, and accessible co-design can create technological systems that champion both personal and collective expression. The unified representation through personality environments, the application of live coding capabilities, and flexible mapping framework enabled a system that could evolve alongside performers developing capabilities and creative goals. Rather than developing generic solutions, this approach enables deep adaptation to individual needs while maintaining connections to broader musical contexts through shared structures. I believe this fusion of live coding, large language models, and collaborative design points towards more responsive and inclusive approaches to musical instrument development, opening new avenues for creative expression, particularly for musicians with diverse movement capabilities. Thank you.
Okay, so yeah, welcome. Today I want to present some of my research of mine, which is about introducing native WebRTC streaming to SuperCollider. We had yesterday a talk about this as well from Bruno, and this is a bit of my take on it. Let's see how it compares. By the way, the project is called Stecker, which is German for plug or jack. But jack is like a bit like already used term, so in order to avoid confusion, yeah. This is still an alpha state. I wished I could have presented a more polished state, but yeah, somehow I got like tracked in SuperCollider development. So yeah, a bit who am I? Like my name is Scheiba, aka capital G on GitHub or D Scheiba on SC-Synth. I wish I could have changed those names, but well, okay. I'm a researcher at the RSH Düsseldorf, so hello to all the people from RSH looking. And I can also spend some time there doing maintenance work on SuperCollider, which is like excellent stuff, or I'm really grateful for having the kind of opportunity there. So what I want to do is like having like a patch bay in the internet. Hopefully it will not look like this, but maybe we can get rid of the wires as well, because we are now cellular maybe. So a project which started prior was this project which I did with Vincent Aubrey, is called Gencaster. Gencaster is a project where I spin up multiple SC-Synth and SC-Lang instances on a server, on a remote server. Like it's a bit confusing now with SC-Synth server and the server on the internet. And I can upload a SuperCollider composition to a graph-based editor, and then use a Janus WebRTC server and some GStreamer in order to navigate to the composition. This also runs in Docker, and yeah, Docker and audio clock and real time is not a good match. Like, not really nice, but it worked. And yeah, it looked like this, or it looks like this. So you can control the composition based on your location, for example, on your user input. This is how it looks from a user perspective, and this looks how it looks from a composer's perspective. Like it's a graph-based editor. It's a bit like a, yesterday when I looked at it again, it seemed like, yeah, it's a bit like a Frankenstein of SC-Lang, Python, JavaScript, carried with some Max MSP and a custom markdown flavor to it. Like everything's inside, but it allows to, I also did my wrote my master thesis about it and did some I called it non-linear sound walks, where I mapped like a Mobius strip around a lake at my hometown. You could walk around it, and I experienced the alternating sounds based on your second rotation. You got a different sound. Yeah, but one thing where I lent this out to a friend of mine, when he used it, he said, yeah, you know, it's great, but what I actually would like to do is have the sound of the, because one thing I didn't mention about Gencaster is it can also access the microphone of the user. It can not just stream from SC-Synth to the mobile phone, it can also stream from the mobile phone to SC-Synth. And he wanted to do like an installation where people can like be in a room, use the microphone array of the people, and process it locally. And that's, yeah, that's one thing that doesn't work. But this is one thing I wanted to change. This is called Stecker. Yeah, yesterday James thought about this analogy between like, yeah, with the drum sampling thing, and yeah, it feels like it. So I started to program my own WebRTC streaming server now. And I think what I wanted to do was to have this as easy accessible to people. And it seems to me that, yeah, we do everything on the server as a UGen, so let's put all the streaming technology into a UGen. And I also thought that we are taking this client-server architecture maybe one step further, because now we're not just passing OSC messages to control stuff, but also audio signals now via the network. And I also have like implemented like a client, which would be like a SuperCollider instance or a mobile phone, but also a server. The server acts as a relay or a broadcaster. So yeah, and one thing I want to do with this as well is like have like a poor man's multi-speaker setup system. Because yesterday you mentioned like you have like to drive around $40,000 of equipment around here, and it's like, yeah, this would be like a cheaper alternative. Not as nice though, but yeah. So how does it look essentially? Although WebRTC is peer-to-peer, we can use it with the server as well. So let's say I'm a client and I want to send to someone else. So I want to send to those receivers. I send my signal by using WebRTC to the server to a specific called room, which is an address essentially. And then I can access from a client this audio signal again. And the client is not, because we're using WebRTC, WebRTC is implemented by every major browser, which is really nice because now we can also communicate with SuperCollider, the audio signals, with the mobile phones. And I implemented different kinds of rooms. Like you have a float room, an audio room, and a chat room. And the float is for the traditional control rates, because like, maybe I should have mentioned the audio earlier. The audio is normally compressed as opus in WebRTC. This has like advantages regarding the size of the stream, but has the not so nice aspect that, yeah, you can't have a DC offset, which is like, yeah, we want a DC offset when we share control signals. So I also have the ability to send plain float signals. And I thought, yeah, why we added, why not add a chat to it? And ownership of rooms is considered via tokens that get generated, or you can specify yourself. So if you have a performance and want to share with the two people want to be the sender, you can tell them the prior password that you're green account or token, and then you can switch. Maybe let's try it out if it works now. I'm having trouble with the Wi-Fi here at Johns Hopkins, so but I felt that using cellular data worked best for me. So let's try if I have signal and not use the Wi-Fi. Okay, so basically, let's I try to start SuperCollider now. Well, it's already started, so here it is. Now I have to remote code, so I don't see it. So don't you see the cursor? So basically what I do is I boot the server, of course. And now I declare my host, which is the server address, okay? Now it's and everything booted, nice. So now let's try to Stecker out, AR, and I give it some signal, sine or FB, maybe something like this or so. And then I specify a room name, okay? And that's it. So now if I go on the website, we will have a demo soon. I just try to have this here. So the problem is the server is in Germany, so there's a bit of latency involved, but now I have the signal on my phone and I can change This one as well gets replaced, takes some time because of we go across the Atlantic and back. But yeah. So that's the first thing. I don't show the demo where I can do the same, but using this as a sender and SuperCollider as the receiver. Trust me, it works. So in order to save some time. So one thing though that I thought would be nice would, because right now I showed a one-to-one mapping, like we have an address and behind this address is like a stream. But I think most of the time we want to have like, yeah, multiple streams available, like that we have one address and then there are multiple streams behind it. And yeah, I implemented something like a dispatcher 2 days ago. It's still really an alpha, but it somehow works. Basically, you specify a regex, regular expression on which kind of room names are matched behind a certain kind of name, URL. And based on this, you get a room associated. So if you work with regex, you most likely know how it works. So let's say I want to connect to the Symposium dispatcher. Okay, it exists, that's fine. Second line is the regex expression. Yeah, the max Symposium does not match because we're not using max here. Then the SuperCollider Symposium 10, yeah, that's okay. The SuperCollider Symposium 25 also works. And now is the question, which one do we take? Well, it's 25. Okay, so then we connect to this. Yeah, so WebRTC, as I mentioned, is a peer-to-peer standard for media exchange. I think right now what Zoom is using is also WebRTC. Implemented for all major browsers, implements some peer-to-peer behind net magic, which I still don't understand after like working 6 months with it. Provides some low latency by using Opus, some Opus magic, and also has the capability, in order you have, in case you have package loss, it can try to reconstruct it, the signal again. Crazy stuff happening there. Opus is only 48 kilohertz, so all the 96 kilohertz guys, yeah, it's not working, but it's already lossy. So from the development perspective, it uses Rust. It's my first Rust project. I found it really interesting in regards to async operations, because like managing async lifetime is like really hard. I don't know how many hard parts of C++ there are, but I found this really hard. And it uses CXX as a binding glue between C++ and Rust, so which works really perfectly. Like I'm really amazed. It seems magic to me that you simply define a interface for it, and it gets exposed as a C interface, and you can just import it, and it just works. Crazy stuff, magic. And this allows that the server and the client, so the user, can share the same code, which is like really nice because I don't have to re-implement everything twice. And the audio is, as mentioned, as used. Yes, let's try it out. Like I set up a dispatcher. Oh, wait 1 moment before you scan it. I need to actually set up the rooms, because otherwise there's no rooms available and you will get an error message that there are no rooms. So what I do is I set up now 32 streams of it. And hopefully it works now. This is like a good beta alpha test. So let's try it out. Please don't use the Johns Hopkins Wi-Fi. It doesn't work. Don't know why. And then you need to click on play. There should be like you get the room assigned. Yeah. Yeah, now I can start to live code this as well. Yeah, but that's nice that it works. Like, has some more problems? It would be interesting to figure out right now. Didn't work for you? I'll get back to you in a moment, and you as well. Perfect, because I know need to collect these setups. I don't have so many phones with me at home, so it's good to test these here. Yeah, let's try to turn it down. See if this works. Nice. So now it should turn on. Perfect. That's better than I expected. Really nice. Wow. Okay, so let's continue a bit with the presentation. I only have some small steps left. Before we go to the questions, I have some pull requests that I really would like to get reviewed. Like one is the WebAssembly build of SCSynth. I would really love to get this in. I think the community would like really benefit from it. It's sitting around since December, like Hans-Holger Rutz did the initial work, and I revisited, like edit RCI and so on. And I also had WebSocket support for SC language, would really add some capabilities to interact with the language from the internet. Has no likes yet, but yeah. Time for questions. Oh, before we have questions, thanks to Leonard, who's my coworker. Thanks to Julian Rohuber, who many know as maybe Telephone for is my professor there. Sam and Ted for organizing this. Everyone remote and on location for making this event, and all the devs over the years, especially James for creating all this, and all composers and performers for all the inspirations over the years. Yeah, if you have some questions, now's the time.
So I didn't catch it. Like, so all the phones were getting different streams.
Yeah.
All the phones were getting different.
Yeah, like there's a multi-channel expansion happening here. I should have showed the code for you. You can read it. So yeah. So basically what I do is like a 32 collect, and I have a Stecker out in it. And I have a room name. Here I can assign multiple rooms and the input signal. And everyone gets, when visiting the website, gets assigned a different room or a random room. So you can implement some different kind of heuristics, like, yeah, do round robin, do random, do any kind of stuff. Yeah, but I tried this at home. It works with 256 streams. It still works. That's a bit like, I found it impressive because you need to have 256 threads converting SuperCollider float32 to Opus. That still works with 256 on like a MacBook with i9. So that's crazy. And the network is not a problem either. So.
Great, thanks. So if I want to run this, what are the three?
So if you want to run this, you can, let's try if the mouse, here's the mouse. Okay, so basically what you need to do is go. Yeah, so here is the repository for it. And I haven't set up like the whole CI so you can download it easily. It's already built. I don't have like this package release management. But build this Eugen, I will maybe set up such as infrastructure that you can download it. And from now you can access my server. If you want to run your own server, there's also the tutorial if you have some Nginx knowledge, how to set it up. It's there. And yeah, I think it's, or the goal of this was to make it really easily accessible to people. And I hope it will be. Like this is alpha, so it will break. And especially because this is network stuff, this is even more radical if it breaks, because Yeah. But yeah, yes, the server code as well. Here's the server code, the Stecker server. And if you want to run your own server, or you can also use my server, which is like the default for now. And then you just install it like any other UGen. Like it does not yet have Windows. Linux, yes. But Windows, I don't have like the building pipeline available to my hands. If someone wants to provide this, I would be grateful for request.
Good, thank you.
I